16.2 is looking at activation energy. So we've been talking about the concept of activation energy and that all particles have to equal or overcome the energy needed to have the proper orientation and the proper energy to break and reform bonds. But we've never actually applied a value to it until now. So as we discussed in 16.1, K, which is the rate constant, is temperature dependent. And so therefore it is a general measure of rate at a particular temperature. And we've discussed this conceptually, and it makes sense, right? So if you increase the temperature within a reaction, so within the system, that's going to increase the kinetic energy available for the reactants to collide. And so you're going to increase the frequencies of the collisions and therefore increase the amount of products made, right? Which therefore increases rate. So we know if we increase temperature, we increase rate. Looking at the calculation itself that we've discussed in 16.1, we know that concentration is not temp affected, right? That's just solely affected on concentration. So therefore, the only thing in the rate expression can be K. And so that is what's going to be temp affected. So the temperature dependence of K depends on the value of the activation energy for that reaction. So if you have a higher activation energy, and so we could go back to the Maxwell-Boltzmann curves, right? That's really bad. And so if we have the Maxwell-Boltzmann curve, and we have a really high EA, so that means there's very few particles that hit it naturally. So if we have a higher activation energy, as we increase the temperature, you're going to increase the number of particles that have the capability of colliding because we shifted that curve, right? So now we have more particles that can participate. Makes sense. If we have a lower EA, so we go through, we have our EA, right? So we already have a lot of particles available for a reaction to take place. If you increase the temperature by the same amount, not as many particles are affected overall, even though my drawings are very bad. So the person, Arrhenius, who came up with a way to figure out how K and temperature interact, so it's called the Arrhenius equation. And this is showing the temperature dependence of K. Here's the equation. It is in your data booklet in table 1 or reference section 1. So K, which is the rate constant, equals A times the natural log, or E, the inverse natural log, to the negative EA over RT. We know K is the rate constant. A is Arrhenius's constant, and that is the frequency factor. So that is how often particles are colliding at what temperature. It has the same units as K, so that that way they can equal each other. It's specifically looking at the successful collision frequency based on the collision geometry and the activation energy. Well, only one of those can we numerically find, and that's activation energy. The geometry can be used with a catalyst or just associated that at an increased rate, we're going to have increased effective collisions with their geometries appropriately. We know EA is the activation energy. R is the gas constant. It's 8.314 joules per mole per Kelvin. Again, that is in your table or reference table 1 of your data booklet. And T is absolute temperature, measured in Kelvin, because the gas constant is also in Kelvin. So keep that in mind, that this is done with the absolute scale. Now, when you go through and you plot that kind of equation, you get a exponential or decreased exponential function, which is very hard to interpret. So by taking the natural log of the equation, that's going to give you a formation of a straight line. And from there, we can manipulate the mathematical equation to determine activation energy in particular. So that's what we're going to do. And that straight line, or this process, is creating what's called the Arrhenius plot. So taking the natural log, so now we have the natural log of K equals negative EA over RT plus the natural log of A. You're like, again, This is not cool. This is a lot of nonsense. Well, let's put this in terms of algebra. We know that a straight line is y equals mx plus b. We're just going to insert this funky material in the Arrhenius plot into y equals mx plus b. So ln k equals y. 1 over t is x. Negative EA over r is your m. And we know m is a slope. And we know that can be determined from a rise, if I could spell correctly, rise over run situation. This makes it a little bit easier to see and to handle and manipulate. So the gradient is what we can measure. All right? So the gradient is going to be the change in ln k, because that's your y, over the change in 1 over t. That did not come out very well, but that's okay, because that's your x. And that equals your m, right? So y over x equals m. And so that's your EA over an r. This is a constant. So your only unknown is EA. Therefore, EA, which is joules per mole, has your measured gradient, which is K, times your 8.314 joules per mole per Kelvin. Because if you take the units of K and divide out temperature, if you take the units here, you end up with K. Sorry. So what does this look like? You could be asked to graph. I haven't seen it, but it is always a possibility. So if it says draw a graph, you have to go through it. So you're going to be given data. You'll be given the rate constant, but you're going to be given it in just regular K. You need to convert that to ln of K. So that's going to be a calculator, natural log of the value they give you for the rate constant. They're also going to give you the temperature in which the reaction is occurring. And that's going to be in degrees Celsius. So you need to convert it to Kelvin and then take 1 over Kelvin to get a value. Then you can draw your plot. That means graph it. Then you can measure your gradient, which is your slope, and solve for EA. So right now, I'm just going to show you the last points and how do we go through and calculate that, because that's what I've seen the whole time when it comes to this topic. So here we have a graph, all right? And these graphs can get a little messy. First thing I want you to do, and I wish I picked a different one, but that's okay. Look here to see that you're working with 1 over t. Sometimes I've seen this saying times 10 to the negative 3, so you need to take that into account. And we'll do some practice with that in class. So now what you need to do is you need to find 2 points on your graph. And I always try to make it the easiest points in which to determine accuracy, because accuracy does take into play. So it's a really messy graph. So I'm going to go straight onto these lines of the 0.00155 and going to take the 0.0016. So I'm going to go down to see where the line hits. It's not easy. Make sure you're following. And you don't have to draw this, but I'm going to just kind of show you what I do. Okay. And then I'm going to draw an arrow down. So instead of rise over run, I'm going to fall over run, and I'm going to go over sideways. Make sure you're using a ruler or you're being very careful. I am struggling doing it on here to make sure you're staying with the exact lines. All right, so at 0.00155, it has a negative 6.8 ln of k. At 0.0016, it has a negative 7.3. And I'm going to fall over run. So that means I'm going to do negative 6.8 minus a negative 7.3 to find that change. Okay, so this is my change in ln of k. And then I'm going to take my 0.0015 minus my 0.0016, and that's my change in 1 over t. Okay? And so when you go through and you figure that out, you get 10,000. So that is your gradient, right? So if we want to look and determine, that's my gradient, so I take 10,000, sorry, and I multiply that by 8.314, I'm going to get 8, my 8s are horrible, 83140. This is in joules, so it's going to be 83.1 kilojoules per mole as my final answer. The only thing I can warn you against, and what I have seen in the past, is not being consistent. So I've seen people rise, right? They go up, and then they go over, but follow the arrows. If you're going to go up, go over. If you're going to go down, then go over. Make sure your arrows are always consistent so that you know your numbers are being put in the right direction of what fall over run or rise over run looks like, run over rise. Just be consistent. The last part of 16.2 is solving simultaneous equations. So EA can be calculated from the K values at 2 different temperatures. So you can run one reaction at 2 different temperatures, and this is so much easier than reading a graph. So if we have ln of K1, we've seen this equals negative EA RT1 and plus ln A. And then we do the same thing for reaction number 2 of temperature number 2. So we're going to combine those equations. And look very carefully when you combine the equations. ln of A disappears. And make sure you pay attention that because of the way the divisions work, temperature 2 minus temperature 1. All right? So you're going to have that in place. So now, if we have temperature 1 equals 283 degrees Celsius, and it has a rate of 3.52 times 10 to the negative 7th. Temperature 2 has a temperature of 508 degrees Celsius and a rate of 3.95 times 10 to the negative 2. All right, so first it has to be in Kelvin, right? So let's convert these to Kelvin. So 283 becomes 556 Kelvin. 508 becomes 781 Kelvin. Plug it in, right? So the natural log, 3.52 times 10 to the negative 7th over 3.95 times 10 to the negative 2 equals EA over 8.314 times 1 over temperature 2, 781, minus 1 over temperature 1, 556. Solve for EA. There's only one variable there. Just make sure you're very careful in manipulating the equation, right? Solve for one side at a time. And then ultimately, you get 1.87 times 10 to the 5th joules per mole. And then what that would equal, then convert it to kilojoules, so 1.87 times 10 to the 2nd kilojoules per mole. And there's your answer. And that is it for 16.2.